Hello guys, welcome to our channel once more. So today we are going to be solving the fastest way we can, Faculty of Engineering and Technology, FET Boya. We're going to be solving the first 50 questions. So I'm going to be teaching you like real hacks on being fast and efficient in the exams. Let's get Friday. All right, which of these physical quantities has its base unit kilogram meter squared per second squared? Now take a look at this. You have kilogram meter per second squared. That's already force. When you multiply force by another meter, that's basically distance. So you have now kilogram meter squared per second squared, which gives you energy, force times distance, which is work done, right? So our answer is B. The intensity is defined as the power per unit area. Which of the following is a unit of intensity? Come on. So we just defined that as power per unit area. The power is of course force times velocity, since you just want to get units, right? So you're not really interested in the physical significance of that. So unit of I is force is kilogram meters per second squared. Then we multiply that with meter per second. You have kilogram meter squared per second cube divided by our area, which is meter squared. So our SI unit is kilogram per second cube. So our answer is B. Which of the following combinations has two vector quantities and one scalar? All right, A says vector, so that's not a quantity, forget about A. B says deceleration, okay, that's a vector. Volume, amplitude, these two guys are scalars. So wavelength is a scalar. Momentum, positance is a scalar. Moment of a force, that's a vector. Momentum, vector. Speed, all right, so two vectors for one scalar. So our answer is D. Magnitude of an acceleration of an object moving along a straight line is equal to V. Alright, so we basically define acceleration like A equals dv dt, right? So if A is already dv dt, so this is basically the slope of velocity time graph, right? So our answer must be C, the slope of its velocity time graph. Alright, a system which can attain resonance A oscillates with large amplitude. Alright, when a system is actually at resonance, right, so its amplitude of vibration is actually largest, but it's not we're talking about the possibility of a system attaining resonance. We're not talking about a system that is already at resonance, right? So the possibility of you attaining resonance, this is not quite a possibility, right? Because we need some other parameters, like maybe there's an oscillator, right? There's a driver that's driving the oscillating system, such that the oscillating system oscillates with the frequency of the driver, right? So if the frequency of the driver now equals the natural frequency of the oscillating system, then resonance occurs. So, and we know that resonance, of course, there's maximum amplitude, but this is just a situation, that like a fact about resonance, not a condition for which resonance should depend on, right, for its occurrence. So B says oscillate at its natural frequency. Of course it should not, it should rather oscillate at the driver's frequency. So if the driver's frequency is now equal to the natural frequency, boom, then resonance. But the system itself should not be vibrating at its natural frequency. It should be vibrating with the frequency of the driver, which is basically you talk about forced vibrations. So that system is performing forced vibrations whose frequency is equal to the frequency of the system that is forcing it to vibrate, right? All right, so so this is not true. C says encounters very little damping. D says performs forced oscillations. Correct. All right, C, oh god, this C just talked about encounters very little damping. All right, so we know that at resonance we just expect that the frequency of the oscillator should be, the natural frequency of the oscillator should be equal to the driver's frequency, right? So we have nothing to talk about damping, right? So damping is really not a necessary condition for whether or not resonance occurs. All right, so we actually have D performs forced oscillations. Perfect. So that system has to be performing forced oscillations, and the driver has to have a particular frequency of oscillation, right, such that at some point that force frequency equals the natural frequency of the mechanical system. Boom, resonance occurs. So it has to be performing forced oscillations. So our answer is D. Okay, at the instant the bulb of an oscillating simple pendulum reaches the equilibrium position, the displacement is 0. Which of the following statements correctly describes the kinetic energy of the bulb and the tension of the thread from which it's hanging at 0 displacement? All right, so this is how a pendulum normally went to displace, right? So it has to move, it has to swing. We're talking about a point where it actually has 0 displacement, which is equilibrium position. So, but then let's just resolve the forces. So we have the tension here, the weight is acting vertically downward. If we resolve this weight, we're actually going to have mg cos theta over here and then mg sin theta. Right, so this is like the restoring force that's trying to bring back this bulb to the equilibrium position. So we see that T minus mg cos theta, of course, produces the centripetal force, right? The resultant force towards the center, right, is a centripetal force. So T, of course, is mg cos theta plus mv squared over r, right? So when is this tensional force maximum? Now, before I come there, let's just get kinetic energy first. We're going to say kinetic energy is, of course, half mv squared. So our Ke is half m. V for a particle oscillating in simple harmonic motion from its equilibrium position is actually omega r equals omega t. All right. So we square that. So we're actually going to have the Ke to be this. Now you notice that the Ke here, I've already displayed the answer to be B. So maximum kinetic energy and maximum tension. Now we're talking about equilibrium position, right? So come here. At equilibrium position, of course, that's when the particle is at rest, right? So theta here, this angle the particle makes from this vertical is actually 0. So we put in 0 here. We actually have, of course, 0. We actually have 1. So you notice that the kinetic energy is maximum at this equilibrium position. Now if we come over here, and then we put 0 here, right, we are going to have T equals mg plus mv squared over r. Now you notice that cos theta ranges between -1 and 1. So this cos theta is actually maximum when cos theta is 1. Right, so if so to get the maximum possible value for T is only going to occur when this cos theta is actually 1, and that's when theta is 0. So when this bulb swings back to this equilibrium position, our tension is maximum and this kinetic energy is also maximum, because our theta basically is omega t. So you notice that our answer B is consistent, right? Transverse waves can be distinguished from longitudinal waves using, of course, polarization, because every other form of wave, all of these properties, the waves can undergo, right? Refraction, reflection, diffraction, all waves can do that. But transverse waves can be plane polarized, longitudinal wave cannot. We have 2.5 kilogram of water is heated in an open container for 5 minutes using a heater. So you just pause the question and read the question, pause the video and read the question, right? So we have heat supplied by heater is, of course, heat gained by water to change temperature plus convection and radiation losses. Yeah, because part of that heat will be wasted because it's an open container, right? So yeah, convection and radiation, perfect. We actually therefore have that our Q is mc delta theta, right? That's the heat supply, but this Q is actually power times time, so we actually make delta theta the subject, so we have PT on mc like that. So substituting the values, we actually have our delta theta to be 57.1 degrees Celsius. Now ideally you expect this temperature change to be lower. Why? Because not all the heat supplied by the heater goes to raise the temperature of the liquid. Part of it is lost to convection, convectional losses and radiation losses, right? Good. So the heat change should actually be smaller than this, but you don't have an option like that, so the change in temperature of the water is 57.1 degrees Celsius. All right, so that's the answer. So we go ahead. Our answer is, oops, okay, that's a mistake. The answer is actually B. Which of the following is correct for a body giving out heat? So we're just going to produce that counter cases here. So option A. The counter case A says its temperature always drops with time. That's not true. What's the counter case? Change of state, water to ice at 0 degrees Celsius. Because when ice is becoming water, right, it's gaining heat, right? So which of the following correct for a body giving out heat? Oh, okay, so that's giving out heat. So basically this is water to ice. Yeah, water to ice. So you're giving out heat and you are not changing temperature, right? Because of course you are giving out latent heat. Perfect. So of course your temperature stays constant and it does not change. So A is not true always. Its temperature should be constant. Oh, that's not true always. Hot water allowed to cool in air. So if you're cooling water maybe from 100 degrees Celsius to maybe 30 degrees Celsius, that process, right, the entropy change as associated with that process actually mc delta theta, which is a function of the change in temperature, right? Good. So C says it cannot be in thermal equilibrium with any other body. Now let's look at the counter case I produce here. At thermal equilibrium, zero temperature gradient exists between the system and its surrounding. So if it's still losing heat, then the system is not in thermal equilibrium. You get, right? So if the system is losing heat, like the question is talking about, the body is still giving out heat, then it's not in thermal equilibrium with the system, with its surrounding. So D says it has lower heat capacity than its surrounding. Well, not necessarily, right? Hot water poured into a metal can into a metal can will warm it up, and vice versa, right? So what I'm saying basically is the can obviously has a lower heat capacity, right? It requires a very small amount of heat to have a unit change in temperature. But the water has a higher heat capacity. So hot water will be losing heat to the can, which has a lower specific capacity. But if the can is rather hot and the water is cold, the can now loses heat to the water, right? So our answer here is actually C. So it cannot be in thermal equilibrium with any other body, right? So cannot. If it's giving out heat, then it cannot be, right? Because we require it to be, for you to be in thermal equilibrium, then there's no temperature gradient between you, temperature difference between you and your surrounding, right? So if you're still giving out heat, then you cannot be in thermal equilibrium. Perfect. All right, so you just go ahead and read the question. So the answer is already A. So I'm just going to solve it here very quickly. Power times time, which is the heat supplied to the ice. So this is actually like change of state, right? Because you're melting ice, so we can do that multiplication and compute and form those equations and our x, right? When you double the current, right? So when you double the current, since the entropy is actually a function of square of current, so you expect that more ice, like if you're doubling this current, then 4 times the initial mass of ice that was melting per unit time would now melt at a doubled value for current, right? So we actually have 40 grams then. All right, so then you can just go through and notice the way I've solved it using basic entropy equations, right? Thermodynamic equations. So we have which of the following statements is correct? During a change of state, all right, so the internal energy of a system increases. Not necessarily. Well, that's actually wrong for change of state, because if we have dq equals to du plus dw, right, dq will be ncv delta t. So change of state, change in temperature is actually 0, right? Temperature is constant, so delta t here is actually 0. So we have just dq equals dw. So we actually have that this option A is not correct. So the internal energy of the system increases. It does not even change. It does not change. So du is actually 0. So yeah, A is off. B says latent heat is absorbed. Well, latent heat is absorbed when bonds are broken, right? E.g., when you move from liquid water to steam. It is released when bonds are formed. All right. So we're moving from gas to liquid water. So the hot steam gives off what? Latent heat, right? So it's not always absorbed. That's just what I'm saying. For change of state, it's not always absorbed. Sometimes it's also given out. It's released sometimes. So that's a counter argument there. C says work is done and bonds are broken. Well, not all the time that bonds are broken. Bonds can be formed. If you're moving from, let's say, ice to water, right, then bonds are broken, right? But if you're moving from water to ice, then bonds are formed, right? So yeah, not all the time bonds are broken. So D says work is done and all bonds are being broken. Correct. So yeah, either bonds are broken, either bonds are broken or they are formed, right? So steam to water, bonds are formed. Water to steam, bonds are broken. All right, so our answer is D. All right, a wire M of diameter is joined to another wire N of the same material. The diameter N is out. Okay, so just pause and read. So we actually have these are the two wires M and N. The diameter of M here is of course 2 times that of N. So we actually have the current expression is I equals never, right? N here is charge density in the wire, right? So charge on electron, E, V is the drift velocity, A is the acceleration. So if you get drift velocity, we have that. We have it at that. So we get the ratio of their drift velocities. So the current here would be the same for both wires because they are in series, right? So this is a series connection. They are joined together like this. All right. So and then a common voltage applied across them. Now the charge density here should be the same since the current that flows through them is the same, right? So because basically current is basically the number of charge, right, that's flowing per unit time multiplied by the electronic charge on each of those charges. That's current, right? So if the same current flows through these two wires, then the charge density on each of them should be equal, right? To make the current to make the current the same. So we can actually have Vn over Vm like that, this ratio, right? So we actually have I all of this is associated with n times, so reciprocate when we're getting that for m. So all of these things now for m go up, and then I comes down, right? So we can basically realize that we have this n, right? The charge density, it goes away with this charge density up here, and then E goes away, so we actually have I goes away, A over M over AM over AN. So the diameter of this guy is actually 2 times the diameter of n, so we actually have pi 2d squared on 4 times 4 pi d squared, right? Reciprocate and multiply. Okay, so we actually realize that our Vn is actually 4 Vm. So the velocity of that guy, so B is our answer. Okay, so which of the following statements about silicon Pn junction diode is true? All right, so this is a p-type, right? So it has majority charge carriers to be the holes, right? And the n-type majority charge carriers are the electrons. So when you take these two crystals and then you link them together, like I've linked them here, so there is a boundary at the surface here. Now what's going to be happening is that the majority charge carriers here, the electrons, are going to flow across that boundary and then diffuse some of the diffuse through the boundary and then neutralize some of these guys here, right? So this n-type is basically you're talking about trivalent atom that is lacking in electron, right? So when these electrons come in, so they actually make them like uniquely negatively charged, right? Because they have excess of electrons now, so you have negative charges here. So when those electrons are leaving, remember that they are leaving a pentavalent atom, right? So the pentavalent atom becomes an ion, right? Positively charged ion. So you notice that along this, very close to this boundary, we are now having an accumulation of positive ions and negative ions. So this accumulation actually creates a barrier PD. So you get to a point where charges, these negative electrons can no longer cross this PD to move across. So basically that's the Pn junction in a very short, simple sense. So yeah, so we can talk about forward bias and reverse bias, right? So and all those other things. So that this layer like this, where this stuff is set up, is called a depletion layer, right? Good. So let's just see the options. The majority, so A says the majority mobile charge carriers in the n-type section of the diode are electrons, correct? While the minority charge carriers in the p-type section of it are holes. No, that holes are majority in the p-type, right? So B says, so A is off, A is wrong. B says the net positive charge at the end of the depletion layer is in the p-type of the diode. That's not true. At the end of this depletion layer, the net positive charge is rather at the n-type. Look at this depletion layer. Net positive charge here is at the n, right? So this is our n-type, so the net positive charge. Good. So B is off. C says the majority mobile electrons in n-type section of the diode come from the donor impurity atoms, correct? Right? While the holes are majority charge carriers in the p-type section come from the acceptor silicon atoms, correct? All right, so we have the holes in the n-type section, so that's the holes in the n-types, in the n-type section of the diode are known as free mobile holes. Screw that. So there are very few holes there, so majority are just electrons, right? And these holes are very few. They're just basically thermally generated charges, really. All right, so our answer is C. All right, so Rutherford alpha experiment. All right, so this Rutherford alpha experiment here in a very nutshell. So we have an alpha source like radium, right? So alpha particles projected to maybe incident on a goal for, right? Most of them actually went through undeflected. So this is like a photographic plate, right? So a photographic plate would actually brighten up when maybe a radiation strikes on it, right? Like an alpha particle. So this is radiation. So when it falls on this photographic plate, it's going to glow, right? Good. So we actually notice that if we incident this guy and if many of them go through, then you have many dots behind the goal forward, and that's actually what happened. So you have few other dots at very extreme angles, and that tells you, well, a lot of things. And this actually, our answer has a nucleus of very small size, because many of the alpha particles actually went through. Then of course an atom must be made up of largely empty spaces, right? So yeah, the nucleus must be very small in size and very high density. Yeah, the few guys that actually struck the nucleus actually got reflected at very large angles. The alpha particles are quite a massive particles, so if they are being reflected or deflected through large angles like this, then the nucleus must be very small, reason why many went through, and then highly massive, reason why they are deflected at very large angles, right? And also positively charged, of course, but that's not mentioned there. So our D is our best answer. Okay, so which of the following is true for a body moving in circular path at constant speed? The only reason why you move in a circular path have a centripetal acceleration, because every particle that moves in a circular path has a centripetal acceleration, but you are at constant speed, is simply because the acceleration vector and the velocity vector, this is a velocity vector tangential, right, to this path, they are at right angles to each other. You know the circle theorem where you say the diameter and of course the tangent shall always perpendicular to each other, right? So this vector like that, since it goes through the center of the circle and then to the other side, that's actually like the diameter vector, right? So these two guys are right angles, so there's no component of acceleration along this line, so the speed stays constant, but the velocity is changing simply because it's changing direction. So our answer there is just A. In a radioactive decay, radioisotope emits an alpha particle quickly followed by a beta particle, the resulting daughter nuclide. Alright, so I mean that's just it, right? So these are our equation. So the resulting daughter nuclide is this guy. The nuclear number is actually 4 less, so has a nuclear number reduced by 4, correct? Right? Yeah, our answer is D. Every other one of those guys just. Alright, a body moves from P1 to P2 gravitational field. Which of the following statements about the gravitational potential energy is correct? So A says the change GP depends on the path between P1. It does not depend on the path. Gravitational field is a conservative field, so it does not depend on path taken. The change in GP is dependent on the mass of the body. Of course not. It depends on the relative coordinates between the points where the mass is moving, right? And two of the mass, but if we are talking about gravitational field, then we are really talking about what is it about that field that determines the amount of work that is done, and it is those relative coordinates. So C says the change in gravitational potential energy is equal to the difference between the kinetic energy at P1 and the kinetic energy at P2. Not necessarily. Why? Because you can actually, part of that energy can be used up to overcome frictional forces in the air. Okay, so this is not always true. If it's only true if we neglect, or we have a scenario where we are moving through a vacuum in a gravitational field. Perfect, then that holds. All right, so the change in GPE depends on the relative coordinates. Correct. Our answer is D. The point charge of magnitude Q is moved from one point of M to another N. If its journey between these 2 points lasts for an interval of time T. Alright, so work done is basically FD. So F is equal, right? That's a force, the electrostatic force that's acting on a charged particle of charge Q, right, in an electric field of field intensity E. Alright, so we actually have, but the field intensity itself is the same as V over D, right? So we actually go ahead and then we say this D goes over this D, so we basically have that work done to be VQ, right? Yeah, so our answer is B. Right. Two power plates carrying equal but opposite charge are positioned so that at S. Alright, so power plate capacitor, just keep reading the question. So this is our power plate capacity also. Let's just rule a line somewhere in the middle. So somewhere in the middle where we're talking about midway, right? So midway, so the distance now from one of these plates to this particular point is basically d over 2, right? So we can get the resultant electric field here. How do we get that resultant electric field? If we put a test charge here, a test charge is like a unit positive charge, so we put a unit positive charge here. This plate will be repelling it. This plate that will be repelling that unit positive charge towards this plate, and this plate will be attracting it. So it means that the resultant field here is to the negative plate, so they are basically enhancing each other, right? So you basically be summing the electric fields between those plates. Yeah, so the resultant field is the sum. So if the resultant field is actually E, like the question said, at midpoint, so how do we get that? E1 is KQ over R squared, where R is the distance between the two charges, right? The reference charge bodies. So yeah, we have that plus that, right? So it basically gives us 8KQ on D squared. That's equation 1, because that's midway. Now if we double this distance from this midpoint to any of these places, if we double that, then you notice that since this one was only D over 2, you double it, it becomes D. So you have now D here, and then you also have D here, right? So we can go ahead and form equation 2 now. So our new field intensity at midpoint will simply be summing up these two guys, so which gives us 2KQ over D squared. Now you notice that this new, right, is this E here divided by 4. If I divide this guy by 4, I actually have this. Good. So our A new is E over 4, so our answer is C. So a particle, so just read the question, pause it and read. So the centripetal force provided by, of course, the magnetic force, right? So B equal V, but our speed here is U, so we're going to have B equal U, and then we can strike through one of these U's, all right? And then simplify. Our U is that, but U is actually 2 pi FR, right? So our F is B equal over 2 pi M, so our answer is A. So, which of the following quantities associated with Kirchhoff's first and second laws respectively will be the principle of conservation? So, first law, summation I equals 0. Second law, summation E equals summation IR, right? So, work done in converting other forms of energy into electrical energy per unit charge leaving the source is equals to work done in converting electrical energy into other forms of energy per unit charge entering circuit load. So you notice that this is basically a conservation of energy, and then this guy is basically a conservation of charge, right? So our answer there is C. All right, you can pause the video and read the question. So the energy equivalence of the mass difference is referred to as in the nucleus. The mass difference is associated with a particular energy, which is known as, of course, the binding energy, right? So the energy that is required to completely separate the nucleons. All right, that's it. Okay, when a beam of light is incident on a diffraction grating, red light is deviated most because in the visible spectrum, red light has, well, the longest wavelength. That's for diffraction gratings. But if you talk about dispersion spectrums or spectra, for dispersion spectra, the guy that is actually deviated most, right, is the guy with the shortest wavelength instead. Therefore, diffraction grating, the one that is actually deviated most is the guy with the longest wavelength. You just need to know that, right? So we're talking about dispersion spectra, then the guy that is deviated most is the guy with the shortest wavelength instead. For diffraction, the guy that is deviated most is the guy with the longest wavelength. So yeah, our answer is B. All right, so which consider the statements about capacitors connecting in series in circuit which is in the process of charging. All right, so this was capacitors being charged out by V here. So if they're in series, then the charge on each capacitor will be the same. So one says the charge on each capacitor is the same, correct? The effective capacitance of all the capacitors is less than the individual capacitance is correct because they behave like resistors in parallel, right? Correct. So 3 says the voltage across each capacitor is the same. That's not true. That's why you have V1, V2, V3. Each capacitance C1, C2, C3 have their unique voltages. So our answer here is A. An ideal gas absorbs 1000 joules of heat. Man, so I've just already done the calculations here. So dq equals to du plus dw. Du is how much in change in internal energy we have. dw is work done, right, by the gas. So dq is the heat absorbed, which is 1000 joules. The equation I've told you. But dw is p dv. So p is 20 kilopascals, right? So we actually have dv is that. So our work done by the gas is 500 joules. Now, if we want to calculate change in internal energy, we would simply take dq minus dw, so it gives us 500 joules. So our answer is B. Which of the following statements about the first law of thermodynamics is so are true? All right, first law is basically dq equals du plus dw. Let's start with statement 3. Statement 3 says that the internal energy change in a system, which is this du here, must be equal to energy absorbed by the system. That's not true. Energy absorbed is shared between change in internal energy and amount of work done by the system, right? Unless the system is actually an isochoric thermodynamic system, then this work done is actually zero for isochoric thermodynamic system. You don't want to call them isochoric, you can call them isovolumetric. Iso means constant, choric means volume, or volumetric means volume, right? So isobaric pressure is the same, right? Isochoric volume is the same, and if volume is the same, it means that work done by the gas is actually zero, right? So it means that all the heat absorbed simply goes to change the internal energy, but that's not always true. It has to be an isochoric system only. So the internal energy change in a system must be equal to the energy absorbed by the system. Wrong. 2 says the efficiency of an engine can be greater than 1 if and only if there is no energy. Forget. Can never be greater than 1, right? So 1 says the amount of energy received by a system is always greater than the work done by the system. Correct. That's why the efficiency we would never be 1, right? Because amount of energy that the machine receives, that's power input or work input or energy input, is always less than energy output, right? Good. So 1 only is the answer. So our answer is C. So, which of the following statements can be explained by the second law of thermodynamics? So, statement 3 says heat does not flow from a cold to hot object. Correct, right? So heat cannot spontaneously flow from a cold to hot object unless work is done, right? So we have 2 says the entropy of the universe changes with time. Of course it changes, but how does it change? It has to increase with time, right? It has to increase with time. So because of course second law of thermodynamics can be stated as the entropy of a system can never decrease. So it means that it changes with time, but that can only be an incremental change. So this too is really vague. It's really vague, but because the second law states that the entropy can actually change with time, which is an incremental change, I'll take it. I'll take it, right? Because that's what the statement of second law states. It has to change with time, but the change can only be increased. All right. So net heat flow only in a particular direction in the universe. Oh, come on, in every direction, as long as there's temperature gradient between the two bodies, right? It flows from the hotter and colder, and it can flow in the reverse direction if work is being done, for instance, in your refrigerator. So one is off, so off. So in fact, B is what I think is the answer, but honestly, it's really debatable, and I mean, I argued myself a lot before taking this B. I just don't want to prolong the video. Okay, so a pipe of length that is open at both ends. So okay, we have both ends like this, so we can actually derive that the length here, this antinode to antinode, so the length is lambda on 2, right? So we can deduce that and get the frequency, which is speed over wavelength, and wavelength here will just be 2L. So we can do the same for the second harmonic frequency. This is the second harmonic frequency, and even the third. So you notice that all of these guys, second is 2F1, the third is 3F1, the end will be NF1, right? So there's that relationship, right? So our answer is A, because A says one says the fundamental frequency F0 is larger than F. What? No, this is a mistake. Larger than F2, that's not true. F2 is larger than the fundamental frequency. 2 says the fundamental frequency F0 is the same as F2, that's not true. 3 says the fundamental frequency F0 is half F2, correct? So 3 only is correct, so our answer here is D. So sorry guys, that's not A, it's D. Okay, so we move on to the next. Consider the following statement about mass spectrometer. Okay, so this is like a picture of what a mass spectrometer would look like, right? So you have the ions being accelerated in an electric field. So these are our electric field like that. Then once they get into the magnetic field will deflect them, right, onto this photographic plate. So this is a photographic plate like that. Once these charged particles fall on this photographic plate, it would glow. So you can tell how large the arc, all right, the radius described by this path when it gets into this magnetic field, how large it is as a function of its mass, and also as a function of its the charge, the magnitude of the charge on it, and also maybe its velocity, right, and some other things, and even the magnetic field strength here. All right, so we're just going to deduce that in a moment. So QV equals to half mv squared for electron in electric field. So that's how they are accelerated, right? Good. So work done in changing the velocities, of course, QV. So we can get V squared to be that, and then for magnetic field, centripetal force provided by the magnetic force. So we can get V squared to be that. We equate those two velocities, and then we simplify, and then we notice that Q over M is actually 2V over B squared R squared. So our answer is A. A says the electric and magnetic fields are arranged perpendicular to each other. That's true, right? Because you have positive to negative here, so the electric force is along like this, but this magnetic field is out, right? So I mean, it's like leaving your screen into your eyes, and then this guy is along your screen. So you will notice that those two guys are right angles to each other. And then 2 says the mass charge ratio M on Q is inversely proportional to the radius arrow of the circular path of the charge. Okay, so this is Q over M, so it's inversely proportional. Oh, that's not true. That is not true. So A is definitely not the answer. All right, so let me explain why A keeps popping up as the answer. Is because when I was producing the slides, right, I just copied A as the answer for all of the slides. So what I needed to do was be editing the answers, or the one that the answer is D, I edit off the A. So when I forget to edit, then the answer will automatically appear as A, right? Until I'm discussing it now and I'm realizing that, oh no, I did not edit this one, so the answer was supposed to be maybe B or D or C. All right, so you get the point. All right, so let's just discuss what the answer is. So the electrical and magnetic fields are arranged perpendicularly to each other, correct, like you can see here. 2 says the mass charge ratio is inversely proportional. So of course that one is clearly wrong. Even if you come over here like this, you come over here, the mass charge ratio, this is the mass, this is the charge, so it will be directly proportional to the radius, not inversely. The velocity v in the circular path is independent of the magnetic field. That's not true. The velocity, look at the velocity here in the magnetic field, depends on the magnetic field intensity. This is it here, right? So it's not independent. So one only is correct, so our answer is C here. Answer is actually C. All right, in an RCL circuit, the current in the circuit is, all right, is that, so one says that is the impedance of the system and has the unit of ohm. Correct, very correct. XL is the reactance of the inductor, XC is the reactance of the capacitor, and then of course R is the resistance of the resistor. So A2 says a maximum current flows in the circuit if XL equals to XC. Very correct. For I to be maximum, this guy has to be minimum. When is this minimum? When the reactance of the inductor is equal to the reactance of the capacitor. This guy cancels out, so we are left just with the resistance of the resistors. This when that guy is maximum. So 2 is correct. The resistance R at the resonance point is always 0. Of course, R does not change. It's not it's not a varying commodity in that circuit. Only XL and XC are varying because they depend on the frequency and other things, right? So yeah. So our answer is clearly A here. So we cannot get that one wrong because okay, so they're asking us the base unit of GR. All right, so the base unit of G, basically you just compute, right? Just cross multiply and then do what I've done. So it's per kilogram meters cube per second squared, and our answer is B. All right, so we have the displacement of a particle performing simple harmonic motion with an angular velocity is given by that, where it is the total distance covered by the particle in 2 cycles is. So the question is, what is the distance? Did you hear that? Distance, not displacement. So what's the distance covered for 1 full cycle? All right, let's say that it's oscillating from its maximum position to the equilibrium and then to the other side of the maximum position, like the simple pendulum now. So you have to go from this maximum position A all the way to the maximum position at B and then back to A. That's 1 full oscillation. So what is the distance covered? So from our maximum position A all the way to the equilibrium position, we have covered the maximum displacement of capital A here. Now from equilibrium position all the way to B, has covered another displacement of capital A because we are talking about distance. Okay, distance of capital A again. So from that position B all the way back to the equilibrium position is another A. From equilibrium position back to A is another A. So that's 4 A's for only one complete oscillation, right? So for 2 you actually have 8 A's. So our answer is A. Okay, a ball is thrown vertically upward. So that returns to the value of the acceleration of the ball at the highest point, which is, all right, ball thrown vertically upward is actually a projectile, right? Projectile is anybody that is given an initial impulse and they're allowed to move under the influence of gravity alone. So the acceleration of that body is basically the acceleration due to gravity, which is always 9.8 meters per second squared downwards. So our answer is A. All right, a diffraction gradient with that and that blah blah blah. All right, so these are like our diffraction gradient. This is a picture, right? So you actually have this our grading here. We have light incident on it normally, right? So we want to get the maximum possible number of orders that can be seen here. So you find this value of m, right? So if m is equal to 2, let's talk about second order, right? But you have to understand that these orders are formed on both sides of the screen. This is our screen here. So how many fringes will be seen? 1, 2, 3, 4, 5. There'll be 5 fringes, but if you're excluding the central fringe, then there'll be 4 fringes, right? Good. So we have d sine theta equals to that, and then we simplify. Of course, d here is a reciprocation of the diffraction gradient specification. So our diffraction gradient specification is 600 lines per millimeter. So convert that to 600 lines per meter, and then you reciprocate it, then you get d. So our m now is d over lambda for maximum possible order. So sine theta will be 1. So we get now this guy to be 2.7. So m is basically 2, right? So if m is, you never round up. So if m is 2, so it means that the second order is actually possible, and the second order corresponds to how many fringes? So 5 fringes, but excluding the central fringe, we have 4 fringes. Our answer is B. A simple pendulum oscillates such that it takes 4 complete oscillations per second. The length of such pendulum is therefore, All right, so T is 2 pi L on G, so we basically make L the subject and then we substitute in those values. So period here would be 1/4 because 1 second is the time divided by number of oscillations for that time is 4 oscillations. So we actually have L to be that, which is basically 15.5 millimeters, and our answer is B. Which of the following statements is correct? All right, so the correction here is which is not correct. All right, so it is possible for the speed of a body to change without the body accelerating. That's not possible. It's not, because how do you define acceleration? The rate of change of velocity. As long as the velocity is changing, then the body is accelerating. All right, but speed is just like the magnitude of velocity, and if that magnitude is changing, even bigger reasons why the acceleration must exist. All right, so A is clearly wrong, right? So they say which is not correct, remember. So all these other ones must be correct. So B says it is possible for the velocity of a body to change with a change in speed. Correct. As long as the velocity is changing, speed will change, because speed is a magnitude of velocity. So if the velocity changes, then speed will obviously change. C says it is possible for a body to be accelerating while traveling at constant speed. Correct. The case of circular motion, right? Good. Yeah, so D says it is possible for a body to be moving with resultant force acting on it. Yes, that's Newton's second law. Correct. So so our answer is actually A, because the one that is not correct is A. All right, which of the following force between 2 point charge object doubled if? All right, so our answer is already D, but let me show you why. So F here is K cure 1 cure 2 over R squared. So what will double this force? If this cure 1 cure 2 becomes doubled, then this force doubles, right? The product of these charges, not the charge on one of these guys. If the charge on one of these guys doubled, then the force here becomes 4 times. So if this product is doubled, then the force doubles. Or this distance here is, all right, there's no case where unless we actually have a factor of root 2, right, then you square that, or 1 over root 2 actually, and then you square that, then the force will double. Yeah. All right, so otherwise the answer is just D. Okay, one scalar, two vectors. Our answer is C, right? In an electric field of strength that carries through distance, the work done by the electric force is, all right, so answer is A, so work done is actually force times D, right? So E, force is E cure, field intensity, electric field intensity multiplied by the charge multiplied by D, which is basically just Y. So our answer is A, right? The activity of a radioactive isotope and all of that and all of that. All right, so we actually, the answer is A here. So but n0 over n finite is 2 to the power n. So n0 is actually 100% and our n finite is 68%, right? Because it's actually reduces to 68%. All right, so we actually have our n now to be ln of this, because if you take ratio and then you take ln on both sides, you actually have n to be ln that over ln 2, which gives us that. So you use now the second equation, which is t equals to nt half. So our t half now becomes total time, which is 2.822 hours, divided by our n, which is that, and our t half is 5.07. Okay, a pipe is open at both ends and made to third harmonic. So this one in red means I'm correcting. There was no thing here. There was nothing such that it's harmonic frequency. So you have to be precise. Which one is it? Third? Is it second? So we know that the answer is A already, because I'm using third there. Okay. So Fn is equal to Nf0, right? We already established that from earlier, that for open pipes, the nth harmonic frequency is basically n times the fundamental frequency, right? So we actually notice that F3 is 3F0. So if we're talking about the second harmonic frequency, right, the second harmonic frequency here, then we'll basically just have 2F0 here too. Okay, so if this was second harmonic, we'll just have F2 equals 2F0. So since it's third, so F0 will now be F3 over 3. So this our F3 is 1200 divided by 3 are 400 hertz. That's why our answer is A. So 43. Suppose that the force on the 1 kilogram is that, the earth is and the radius of the earth is about that, then the force on. All right, so the force, now remember that this is variation of g with depth, right? Not height. So G is actually 1 minus D over R G naught. This D here is actually the depth, all right? But what they have given us here, because they said then the force on the 8 kilometer placed at a point 200 kilometers from the center of the earth. This is not the depth, this is from the center of the earth to the particular point. So to get the depth, you take the radius minus this distance, then you now have the depth from the surface all the way down to that point. So the depth is 4,000. So you ratio that depth to the radius, and then you multiply 1 minus that, and you multiply with the field intensity at the surface. So you have this is a field intensity at that particular point. So to get a force now is actually mass times the field intensity at that point. The mass is 8, the field intensity is this, so we have 26.1. But if you are using this G as 10, you would have this exactly 26.7. So the answer is actually A. All right, you can have 26.1 or 26.7 depending on your value of G. When a ray of light passes from glass into air, and okay, so whatever. So refractive index is basically speed in air or speed in glass. That is the refractive index of glass actually relative to air now. So but speed itself is lambda f, wavelength times the frequency. So but the frequency does not change, right? It depends on the source and not the medium through which is propagated. So we must have wavelength in air or wavelength in glass to be the refractive index. So two things can be affected when it moves from one medium to another: the speed and the wavelength. So our answer is C. Okay, a person jumps. This is just application of Newton's second law, summation F equals to mvu on T. So you take that, you substitute, and then you have an answer to be that. So our answer is B. All right, so we're talking about all vectors. All vectors will be B. Torque, impulse, field strength. Those are all vectors. Binding energy refers to the work done in separating its nucleus. Perfect. That's B. 48. Which of the following phenomena can be used to explain the formation of a rainbow? Basically, it's refraction, but reflection is important. Total internal reflection, actually, but the key thing is refraction, because ray of light moving from the air and it's getting through this water droplet. Basically, it's being refracted, right? Because changing, of course, optical media. Okay, so our answer is B. So 49, from the equation that where K is that Boltzmann constant and T is absolute temperature, one can deduce that the unit of this. All right, so the Boltzmann constant is actually measured in what? Joule per Kelvin. So you already know that if this is Joule per Kelvin multiplied by the Kelvin, so this guy must be the Joule, right? But this is actually the formula for translational kinetic energy, so you should know that. So our answer is actually C, energy. All right, guys, thank you so much for watching the video. I wish you all the best in your exams, and hope you stick around to subscribe, and hope you stick around to bring more people to our channel and our content. All right, have fun tomorrow. Wish you all the best.